The wind howls, the temperature plummets. On the vast empty steppe, there is nowhere to hide. For centuries, Mongolian herders faced some of the most extreme winters on Earth. Between the 13th and 19th centuries, nomadic families across the Mongolian steppes endured temperatures that could drop to -40 degrees Celsius, -40 degrees Fahrenheit for months at a time, with winds reaching hurricane-force speeds of over 100 miles per hour, 160 kilometers per hour. Unlike settled peoples who could build permanent shelters from stone or timber, these herders lived on vast, treeless plains where the nearest forest might be hundreds of miles away. Their survival depended on following their herds to new grazing lands every few weeks, carrying everything they owned on their backs. Their solution was the GR, a masterpiece of nomadic engineering that has been perfected over thousands of years. But how could a structure that weighs less than 500 pounds withstand winds that can topple modern buildings? What engineering principles allowed a simple felt covering to maintain comfortable temperatures when the outside air could freeze exposed skin in minutes? How did these nomadic families create a home that was simultaneously portable enough to move every few weeks, yet strong enough to survive the most brutal winters on the planet? From timber in the forests to stone in the mountains, every culture built to survive. This is timber and stone, the foundation of movement, the portable design. Picture a Mongolian family arriving at a new winter campsite as the sun begins to set over the endless steppe. The temperature is already dropping below -20 degrees Celsius, -4 degrees Fahrenheit, and the wind is picking up, carrying the promise of a brutal night ahead. They have perhaps 2 hours of daylight left to transform a pile of wooden components into a warm, secure home. The father and his teenage sons begin unloading the components of their gyr from their ox-drawn carts. What emerges looks deceptively simple. Bundles of collapsible latticework walls called kana, dozens of long wooden poles known as uni, heavy rolls of felt, and a single intricately carved wooden ring, the Toono. Each piece has been crafted with precision, designed to be lightweight, yet incredibly strong. This ability to move was the herders' first and most crucial line of defense against the harsh environment. While settled peoples could retreat to stone fortresses or underground shelters, nomads had to carry their protection with them. The GR's design reflects thousands of years of refinement, where every ounce of weight mattered and every component had to serve multiple functions. The main structural elements work together like a sophisticated engineering system. The kana walls are made of willow or birch wood, chosen for their combination of flexibility and strength. Each section can collapse flat for transport, yet when expanded, creates a rigid circular wall. The uni roof poles are precisely measured, typically 88 poles for a standard family GR, and each one is carved to fit perfectly into the Toono crown and rest securely on the wall lattice. A modern, tiny home of comparable size would weigh several tons and require a truck to transport. The entire gyr, including all coverings and furnishings, could be loaded onto just 3 or 4 camels or yaks. More importantly, a skilled family could assemble or disassemble their entire home in under 3 hours, even in harsh weather conditions. But portability meant nothing if the structure couldn't withstand the relentless assault of steppe winds. How did they create walls that were both lightweight enough to carry and strong enough to resist forces that could reach 2,000 pounds per square foot? The wall of wind, the aerodynamic shape, and lattice frame. The family begins the assembly by expanding the kana sections, and immediately the genius of the design becomes apparent. As each lattice section unfolds, it forms part of a perfect circle, not by accident, but by careful mathematical design that has been refined over centuries. The circular shape is the GR's first defense against wind. Unlike rectangular buildings that present flat surfaces for wind to push against, the GR's curved walls deflect airflow around the structure. Wind tunnel tests on modern GR designs have shown that the circular shape can reduce wind loading by up to 60% compared to rectangular structures of the same size. But the real engineering marvel lies in the lattice construction itself. Each kana section consists of dozens of wooden slats connected by leather joints that allow the wood to flex and move. When wind hits the wall, instead of transferring all the force to rigid connection points, the lattice distributes the energy across hundreds of flexible joints. It's the same principle that makes a spider's web incredibly strong. Despite being made of delicate silk, the web absorbs and dissipates energy rather than resisting it rigidly. The mother of the family moves around the expanding circle, her experienced hands checking each leather joint. She knows that these connections are the heart of the structure's strength. Made from specially treated yak or horse hide, each joint must be flexible enough to allow movement, but strong enough to hold under extreme stress. A single failed connection during a winter storm could trigger a catastrophic collapse. The wood itself is carefully selected. Willow and birch are preferred not just for their availability on the steppes, but for their unique properties. These woods have a high strength-to-weight ratio and natural flexibility that allows them to bend without breaking. The herders learned to harvest the wood at specific times of year when the sap content provided optimal flexibility. Modern buildings rely on rigid shear walls and steel reinforcement to resist wind loads. The GER achieved superior performance using a flexible web that worked with natural forces rather than against them. Each lattice section could move independently, allowing the entire structure to sway and flex like a living organism. The assembled wall creates a perfect circle approximately 16 feet, 5 meters in diameter for a standard family jur. The height is precisely calculated, tall enough for adults to stand comfortably in the center, but low enough to minimize wind resistance. This creates an interior space of about 200 square feet, 18.5 square meters, comparable to a modern studio apartment. But even the strongest walls were useless without a roof that could handle the crushing weight of snow and ice. How did they create a self-supporting dome strong enough to carry loads that could exceed 50 pounds per square foot? The winter blanket layering the felt insulation. With the wooden frame complete, the family begins the crucial process of wrapping their home in its winter armor. The felt coverings they unroll represent months of communal labor and generations of accumulated knowledge about surviving in one of Earth's most challenging climates. The base layer consists of specially woven mats made from reeds or thin wooden slats. These provide a smooth surface and create small air gaps that enhance insulation. Over this goes the felt, thick, dense sheets made from the wool of their own sheep and goats. The process of creating this felt is itself a marvel of traditional technology. In late summer, when the animal's wool is at its thickest, the entire community participates in the felt-making ritual. The wool is first cleaned and sorted, with the finest fibers reserved for the inner layers that will touch the family's skin. The wool is then laid out in thin, even layers and sprinkled with hot water. What happens next is a process that modern textile engineers are still studying. The wool fibers are rolled and pressed repeatedly, causing them to interlock at a microscopic level. This creates a material that is simultaneously waterproof, breathable, and incredibly insulating. The finished felt can be up to 2 inches thick and weighs approximately 15 pounds per square yard. For winter use, the GER receives multiple layers of this felt. A summer GER might use just 1 layer, but winter configurations can have 3, 4, or even 5 layers in the harshest climates. Each layer is positioned to overlap the joints of the layer beneath, creating a seamless thermal barrier with no weak points. The children of the family help position the felt, their small hands useful for tucking the material into tight spaces. As each layer is added, the interior of the GER transforms. The harsh wind noise fades to a whisper, and the temperature inside begins to rise even before the stove is lit. The thick felt walls create a cocoon-like environment that feels almost womb-like in its warmth and security. The insulating properties of this felt system are remarkable. Tests on traditional GERs have shown R values, thermal resistance, of 15 to 20 for the wall system, comparable to modern insulated walls. But unlike modern insulation, the felt also acts as thermal mass, absorbing heat during the day and releasing it slowly through the night. This creates a more stable interior temperature with fewer fluctuations. The felt's natural properties provide additional benefits. Wool naturally wicks moisture away from the interior while remaining water-resistant on the outside. This prevents the condensation problems that plague many modern tents and temporary structures. The material is also naturally fire-resistant and contains lanolin, which repels insects and provides a pleasant, clean clean smell, but the felt covering is just one part of the thermal management system. The outer layer consists of a white canvas or leather cover that reflects summer heat and provides additional weather protection. In winter, this outer layer might be removed to allow the dark felt to absorb solar heat during the brief daylight hours. The completed wall system can maintain interior temperatures of 15 to 20 degrees Celsius, 59 to 68 degrees Fahrenheit, when outside temperatures drop to -40 degrees Celsius, -40 degrees Fahrenheit, using only a small central stove and body heat. Modern homes often struggle to achieve such temperature differentials with far more energy input. The walls were now a fortress against the cold, but they still needed a roof. How did nomadic engineers create a self-supporting dome that could handle snow loads exceeding 2,000 pounds without any internal supports? The crown of the steppe, the compression roof, and Toono. The most critical moment in gear assembly comes when the father lifts the Toono, the wooden crown that will become the heart of their home. This single piece of craftsmanship represents the pinnacle of nomadic engineering, a component so important that it often becomes a family heirloom passed down through generations. The Toono is typically carved from a single piece of hardwood, often birch or elm, chosen for its strength and resistance to cracking. The ring measures about 4 feet, 1.2 meters, in diameter and contains precisely spaced holes around its circumference, usually 88 holes for a standard gear, though this number can vary based on the size and regional traditions. As the father holds the Toono aloft, his sons begin inserting the uni-roof poles into the holes. Each pole has been carefully measured and carved to exact specifications. The bottom end rests in a notch on the wall lattice, while the top end fits snugly into the Toono. This creates a cone-shaped roof structure that relies on compression rather than tension for its strength. The engineering principle at work here is the compression ring, the same concept used in Roman domes and modern stadium roofs. As the roof poles push down and inward on the Toono, they create a ring of compression that actually makes the structure stronger under load. The more weight placed on the roof, the tighter the compression becomes, up to the material's failure point. This design allows the GR to support remarkable loads. Snow loads in Mongolia can reach 50 to 70 pounds per square foot during heavy winter storms. A standard GR roof has a surface area of approximately 200 square feet, meaning it might need to support 10,000 to 14,000 pounds of snow, equivalent to the weight of several automobiles. The compression ring design distributes this load evenly around the Toono and down through the roof poles to the walls. The grandmother watches this process with keen eyes. The Toono she's observing has been in her family for over a century, carved by her great-grandfather and used by 4 generations of her family. Its surface is polished smooth by decades of handling, and small repairs and modifications tell the story of the family's travels and tribulations. But the Toono serves functions far beyond structural support. It acts as the GR's chimney, with a removable cover that can be adjusted to control airflow and smoke evacuation. The opening also serves as the primary source of natural light during the day and provides a view of the stars at night, crucial for navigation and timekeeping for nomadic peoples. In Mongolian cosmology, the Toono represents the connection between earth and sky, the human world, and the realm of Tengri, the eternal blue sky. The circular opening frames the North Star, which nomads used for navigation, and the movement of stars across the opening served as a natural clock. The roof poles themselves are arranged in a specific pattern that has both practical and spiritual significance. The number 88 is considered auspicious in Mongolian culture, and the radial arrangement of the poles creates a mandala-like pattern when viewed from inside the gur. This transforms the interior space into a sacred geometry that reflects the Mongolian understanding of cosmic order. Modern dome structures often require complex steel hubs, tension cables, and sophisticated engineering calculations. The Toono achieved superior strength and functionality using traditional woodworking techniques and an intuitive understanding of structural forces that had been refined over millennia. The roof angle, typically 30 degrees from vertical, is optimized to shed snow and rain while maximizing interior headroom. The overlap between roof and wall coverings creates a weatherproof seal that prevents water infiltration. With the structural shell complete, the family now faced their final challenge: transforming this empty wooden framework into a living space warm enough to sustain life through months of brutal winter. How did they create a heating system efficient enough to warm 200 square feet using only dried animal dung and the occasional piece of precious wood? The heart of the home, the central stove, and heat management. As darkness falls over the steppe and the temperature plummets toward -30 degrees Celsius, -22 degrees Fahrenheit, the family gathers around the most important feature of their new home, the central stove. This simple iron box, no larger than a modern microwave oven, will be their lifeline through the long winter months ahead. The stove's placement at the exact center of the GER is no accident. It represents the culmination of centuries of experimentation with heating efficiency in circular spaces. The central location ensures that heat radiates equally in all directions, taking advantage of the GER's circular geometry to create natural convection currents that distribute warm air throughout the space. The fuel for this stove comes primarily from dried animal dung, known as argol. This might seem primitive to modern sensibilities, but argol is actually an excellent fuel source for the steppe environment. It burns cleanly with minimal smoke, produces steady heat, and is completely renewable. The herds produce a constant supply. When properly dried, argol has a BTU content comparable to low-grade coal and burns with a pleasant earthy smell rather than the acrid smoke of green wood. The mother begins the evening ritual of lighting the stove using dried grass and small pieces of wood as kindling. The children gather around, not just for warmth, but because the stove area serves as the social center of the GER. The father sits on the honored side, the side opposite the door, while the mother manages the cooking and fire maintenance from her traditional position. The stove's design maximizes efficiency through a small firebox that forces complete combustion and a chimney pipe extending through the Toono, creating natural ventilation that provides fresh air without losing heat. The heat distribution in a GER is remarkably even compared to rectangular rooms. The circular shape eliminates corners and ensures no point on the perimeter is more than 8 feet from the central heat source. The family's sleeping arrangements take advantage of this, with the most vulnerable members positioned in the warmest spots. The thermal mass of the thick felt walls contributes to heat retention, absorbing heat during active burning periods and releasing it slowly through the night. This thermal flywheel effect maintains comfortable temperatures even when the fire burns low. The efficiency is remarkable. A typical GER maintains interior temperatures of 15 to 20 degrees Celsius, 59 to 68 degrees Fahrenheit, when outside temperatures reach -40 degrees Celsius, -40 degrees Fahrenheit, using only 10 to 15 pounds of fuel per day. Modern homes of similar size might require 50 to 100 pounds of heating fuel, equivalent to achieve the same temperature differential. The stove also serves important social and spiritual functions. The fire is considered sacred in Mongolian culture, and specific rituals govern its lighting, maintenance, and extinguishing. The eldest woman of the family typically maintains responsibility for the fire, and guests are expected to observe certain protocols when approaching or feeding the flames. But the heating system was just one part of creating a livable space. How did families organize their lives in such a compact area, and what ingenious storage and living solutions allowed them to thrive in just 200 square feet? The living machine, interior organization, and daily life. Inside the completed GER, every square foot serves multiple purposes in a carefully orchestrated system of daily life. The circular space is divided into specific zones, each with its own function and social significance. The area around the central stove serves as the heart of the home, where the mother prepares meals using specialized pots and utensils designed for nomadic life. Everything is lightweight, durable, and multifunctional. A single pot might serve for cooking, water storage, and washing. Sleeping arrangements reflect both heating considerations and social hierarchy. Thick felt mats and fur blankets are arranged around the perimeter, rolled up during the day to free floor space, then unrolled at night in locations that maximize warmth from the central stove. Storage represents a masterpiece of space efficiency. Wooden chests and leather bags line the walls, designed to fit the curved space perfectly. The walls themselves provide additional storage through hooks, loops, and hanging bags that keep frequently used items within easy reach. Privacy in such a small space is managed through social conventions rather than physical barriers. Family members learn to give each other psychological space through positioning and behavioral protocols that are respected as strictly as physical walls. The floor is covered with thick felt rugs that provide ground insulation and create a comfortable walking surface. These rugs often feature traditional patterns with symbolic meaning, transforming the utilitarian space into an artistic environment. Modern, tiny house enthusiasts often struggle to create livable spaces smaller than 400 square feet. The traditional GR demonstrates how 200 square feet can comfortably house a family of 6 to 8 people through intelligent design and social organization. Takeaways: what can modern builders and homeowners learn from these ancient masters of nomadic engineering? Here are 4 key principles that remain relevant today. Aerodynamics over rigidity. In high wind environments, structures that work with natural forces rather than against them often prove more durable than rigid designs. The GR's circular shape and flexible joints allow it to survive wind conditions that would destroy conventional buildings. Thermal mass is key. The GR's thick felt walls don't just insulate, they store and release heat, creating a more stable and comfortable interior environment. Modern homes can benefit from incorporating thermal mass elements that reduce temperature fluctuations and improve energy efficiency. Flexible joints. Structures that can move and flex with environmental stresses often outlast rigid designs. This principle applies not just to wind resistance, but to thermal expansion, ground movement, and other dynamic forces. Centralized radiant heat. A single central heat source in an open, circular space proves remarkably efficient. This challenges the modern tendency toward complex zoned heating systems and suggests that simpler approaches might sometimes be more effective. Don't attempt to replicate traditional heating systems without proper ventilation and modern safety measures. Always prioritize fire safety and carbon monoxide prevention in any heating system design. Conclusion: the Mongolian GR represents far more than ingenious engineering. It embodies a complete philosophy of living in harmony with one of Earth's most challenging environments. For over 1,000 years, these portable homes have sheltered families through winters that would challenge modern survival technology, using nothing more than wood, felt, and accumulated wisdom. As Mongolian wisdom teaches, the GR is not built upon the earth, but with it, moving as the seasons move, bending as the wind bends, yet never breaking. This philosophy of flexibility offers profound lessons for our modern world, where we often try to impose rigid solutions on dynamic problems. The GR's circular design reflects the Mongolian understanding of cosmic harmony, where the Toono opening connects the family to Tengri, the eternal blue sky. The traditional saying reminds us, "He who wants to build high must dig deep," and the nomadic herders dug deep into their understanding of natural forces to create homes that have withstood the test of centuries. The wisdom of the steppes teaches us that true strength comes not from resisting change, but from adapting to it gracefully. As another Mongolian proverb reminds us, "A man falls 7 times and rises 8 times." The GR itself embodies this resilience. A home that bends without breaking, carrying its inhabitants safely through the storms of life. Every structure tells the story of those who refuse to surrender to the elements. Let me know in the comments what impressed you most about these nomadic survivors. What nomadic secret would you bring to a modern home? The aerodynamic shape, the layered felt insulation, or the genius of the compression roof? See you in the next episode.